Hi, I'm Paul. We are doing Leetcode Must Know interview questions. Today's challenge is unique paths 2. Rating is medium. This is going to be another dynamic programming problem, a 2D dynamic programming problem. Although we could also do it as a 1D dynamic programming problem. But the challenge is that we're given an m by n integer array called grid. Actually, it's called obstacle grid. Let me scoot this over for a second. Here's the whole method signature here. Unique paths with obstacles. And we have a 2D array coming in. We'll see an example of what that looks like. There's a robot initially located at the top left corner, like this. Here's the robot. The robot tries to move to the bottom right corner. There's a star here, but that's not an obstacle. That's just like the goal. The robot can only move down or right at any point in time. An obstacle in the grid is marked as a 1, and a space is marked as a 0. A path that the robot takes cannot include any square that is an obstacle. Return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9th. That's 2 billion. That's a hint that it should the answer should fit in an int. So yeah, let's see. Is there anything else that we should know here? Okay, m and so the m and n are going to be somewhere between 1 and 100. And every element of the obstacle grid will either be a 0 or a 1. All right, let's kind of sketch out an example here. Okay, so I drew the obstacle grid. I mean, you can see it over here, but I wanted to be able to see it in matrix format. This is the DP matrix here. All right. This is actually pretty similar to the minimum sum path, where what we're going to do to start out is initialize this top corner to 1. I mean, the robot is already there, so there's one path for the robot to get there. Now, we can move through the first row and the first column, and we can continue to fill those with ones, provided that there's no obstacles. And in this case, there are no obstacles. There's no obstacles in the first row. There's no obstacles in the first column. Oh, you know what I forgot is we really want to initialize the rest of the DP array to 0, because as far as we know, there aren't any paths to these. So we can go across, and if there is an obstacle, we just stop, because we can't go through the obstacle. So anything remaining in the first row, or if we hit an obstacle in the first column, we just stop. We can't go through it, so nothing else in the first row or column, I mean everything else in the first row or column will continue to be a 0 if we hit an obstacle. In this case, there are no obstacles, so we can take these out, we can take this out, we can take this out, we can take this out, and we can put 1, 1, 1, 1. And there's one way to reach each of those cells from the starting cell. All right, now we're going to go row by row, not counting the first column because we already dealt with the first column. So the next cell that we're going to deal with is this cell here in the middle. Now, if we look at the obstacle grid, there is an obstacle there. So we have to leave this at 0 because we can't get there. If there's an obstacle, you can't get there, right? Let's go to the next one. The next one, there is no obstacle in the obstacle grid. So the number of ways to get here would be the sum of the number of ways to get to the cell to the left and the number of ways to get to the cell above. And we add those together and we get 1 plus 0 equals 1. We go to the third row, second cell in the third row. Again, we add the cell to the left and the cell above, and we get 1. There's one way to get to that cell. And finally, in the bottom corner here, we add the cell above and the cell to the left, and we get 2. Right. And that is the answer. Okay. I'm going to add one thing here, and that is we really don't have to maintain a matrix in order to solve this, because the cells in any row are really only dependent on the row above it. That is, by the time we get to the third row, we really don't care about the first row anymore. If there was a fourth row, we wouldn't care about the first row or the second row. Now, each row is going to get merged into the row underneath it. That is, those numbers are going to get added. So if we just kept the same row and only added numbers from the left, we would get the same result. I'm going to clear the drawing here and scroll this, because I don't think that we actually saw that the correct answer was 2. It doesn't seem to be in the, oh, there it is. Yeah, right here. So the answer is 2 for that one. Okay, look at an implementation of this. I'm going to do the implementation a little bit differently. I've done like 100-something of these, and it probably should have occurred to me sooner, but I'm going to do some of the typing behind the scenes and then just share it with you a little bit at a time here. All right, let's see what we've got so far. We're going to initialize a couple of variables here with the dimensions of the grid. We're going to set up a DP array. The size of the DP array is same size as the grid. Num rows, num calls. Now, as we saw, what we want to do first is we're gonna handle the first row and the first column. So for row 0, we are going to go either all the way across or until we hit an obstacle. As long as the obstacle grid is 0, we're going to keep going. And we're going to set cells in the first row to 1. Same thing with the first column. We are going to keep going down the first column, either all the way or until we find a cell that is not equal to 0. And we're going to set those column cells to 1. Okay, now we need a loop for the rest of the grid. All right, so here's the nested loop right here to go through the rows, through the columns, starting at row 1, column 1, because we already processed row 0, column 0. And we're going to look at each cell in the obstacle grid. So if the cell in the obstacle grid at indices row col, if that is 0, meaning that there's not an obstacle, then we can get to it. And the number of unique paths to get to it would be, we can obtain that and put it into the DP array, the DP matrix, by taking the cell to the cell above it and the cell to the left and adding them together. All right. There's no else for that, because the else would mean that the obstacle grid cell is a 1. It's an obstacle. So we're going to leave it at 0. Can't get to it. All right, once we've done all that, the sum should be in dp num rows minus 1 num cols minus 1, which is the bottom right cell. Okay, let's try running this. All right, that works on the simple cases. I mean, I think this is fine. It's the only thing that sort of concerned me was, will ints work? I mean, it should work if we can only get numbers up to 2 billion, but let's submit and find out what happens. All right, that's good. Okay, let's do a quick conversion of this into a one-dimensional, into a 1D dynamic programming solution. Runtime is the same. It's O of m times n. The space is less because we're just using a single dimension array. So we'll say int dp equals new int. And it's going to have to be num calls, right? Num calls, yes, because we're going across. Was new int num calls. All right. We don't need this initialization stuff here anymore, the first row and column, because we don't have columns. But we do need to initialize dp 0 to 1. Say there's one way to reach the first square. All right, now the nested loop, Again, we have not processed the first row, so we need a 0 there. We have not processed the first column, so we need a 0. If the obstacle grid equals 0, then dp at column will equal whatever is already in the dp column, because really we're just merging the rows as we go down. So we don't have to add the sum from, or the number from the cell above. We're just reusing the row. So the number in that, I mean, you could say column, but since we don't have, we only have one row now, but the cell above it would already, the number in the cell above it is already in there. So we add dp. Oh, no. You know what? I need to do this a little bit differently. I need to do this a little bit differently. Okay, let's do this, because there needs to be an else here anyway. But let's say if there is an obstacle, all right, we have to do something a little bit different. And that is because we're merging the rows, then we're going to have to reset this to 0. Okay. In the 2D version, all of the cells are already set to 0. So if the obstacle grid is 1, we just ignore the cell. We don't do anything, and we leave it at 0. In this case, since we're merging rows as we go down, we may have a number in there that's not 0. And if we hit an obstacle, then we're going to have to reset it to 0. But I wanted to add one more thing here, and that is if the column is greater than 0. Because if the column is 0, there is no cell to the left. So we don't want to try to add the cell to the left by, doing column -1 if column is 0. So we've got if the column is greater than 0, then we do have a cell to the left and we can add it. All right. And then the return would be at dp numcalls -1, right? Yeah. Yeah, I believe that would work. All right, let's try that. Uh-oh. 19 error. Okay, let's see. Okay, I've screwed up the brackets here somehow. Let me pause it for a second and find that. All right, I think I see what it is. Actually, there should be a bracket here. Okay, let's try that. And submit. Okay. All right. Runtime. Runtime is m times n. Either way that you do it. If you do it as a 1D, I don't know if it'll let me analyze complexity twice in one day. Usually there's a limit of analyzing complexity once per day. But I don't know if that's like one runtime and one memory or just one total. But in any case, the memory is going to be O of n this time because we did it with a 1D array rather than 2D. I don't know why we're way out, way out here. I mean, there isn't any, well, I mean, there isn't, I don't think there is a way to use less memory than we used. I assume these are all Java solutions, but all right, I mean, I can live with that. So that's it. That is, what is it? Unique Paths 2. I hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.